Okay, good morning, everyone. Let's dive in. As usual, let's talk a little bit about, in this case now, the final project. So tonight, your first of 4 weekly milestones is due, M1. Apologies if I wasn't clear last time. What you're submitting for milestone 1 is in Brightspace 4 very short paragraphs or a couple of sentences describing your planned M1, M2, M3, and M4. What's your final project? How are you going to break it down into 4 bite-sized chunks? And then in addition, you're submitting along with M1 proof that you've implemented your first milestone. All good? Okay, not too complicated. All right, in your description of those 4 milestones, the 4th one mentions preliminary A/B testing. So I just wanted to spend a couple minutes to go back over A/B testing and what counts as preliminary A/B testing. In your case, you're at the end of your you're going to have at least 2 slightly different versions of your algorithm, algorithm A and algorithm B. Algorithm A can be, if you want, it can be A10. It can be the quadruped being evolved for rightward travel using the standard neural network and using, what did we leave off with? The parallel hill climber, I think. Yeah? That can be A if you want, and then you're comparing it to some slightly different version. For example, if you tackle the Brainiac project, which is to add hidden neurons to the quadruped's brain, it makes sense. Version A would be the quadruped without hidden neurons, and version B would be the quadruped with hidden neurons. Everything about algorithm A and B is the same, except that one thing that you're interested in, which is what happens if you expand the brain of the robot? Does it make things easier or harder on the evolutionary algorithm? If you're tackling a different project in which there's a completely different robot body or a completely different robot environment or a completely different fitness function, then having A10 as version A probably doesn't make sense because your version B is going to have a different robot body, a different brain, a different fitness function, a different environment, and so on. That would be what's called an apples and oranges comparison. You can't really compare those 2 versions of an algorithm because they differ in a lot of different ways, and you'll never be able to determine which thing is different. One of the number 1 rules about being a scientist or an engineer is modify one variable at a time to see whether it's that variable that's having an impact on your system. Make sense? Okay. So let's talk now about preliminary A/B testing. Let's take as an example the Brainiac project. So adding hidden neurons to your robot. Let's assume in that case you do choose assignment 10, the baseline experimental platform, as your algorithm A, and you run it for a number of evolutionary generations. So we've got evolutionary time on the horizontal axis, and we've got fitness on the vertical axis, where fitness is, as we left off in A10, fitness is rightward travel or forward travel, whatever it is, displacement. Okay, so you run basically A10 for a while, and fitness goes up, and then as usual, it starts to level off after a while because it gets harder and harder for the evolutionary algorithm to find mutations and crossover events that will produce a faster moving robot. You've built hidden neurons into the quadruped. You've wired up the sensor neurons to the hidden neurons. Maybe you've chosen to add some recurrent connections in the hidden layer, maybe some self connections. You've added some synapses, then also connect the hidden neurons to the motor neurons. You're all good to go. Your robot now has a bigger brain. You do one evolutionary run with the bigger brain, and you get this result. So A is here and B is here. Did it help? Did it help to give the quadruped a bigger brain? Did that facilitate things for the evolutionary algorithm? You see a couple nods, a couple of, I'm not sure. Remember that the evolutionary algorithm has a lot of random operations in it, right? Trial and error. It's hard to really say at this point. It looks good because B is higher than A, but who knows? What we want in preliminary A/B testing is something that looks like this. Just evidence that you can run your code in mode A or run your code in mode B, and you can get back how well or how poorly things went for the evolutionary algorithm in either of those modes. You clearly don't have enough data yet to determine whether or not adding hidden neurons has actually made things easier on the evolutionary algorithm. So between your submission of M4, the fourth and final milestone, and our exam period, when you're going to present your results orally in class, during that time, what we hope is that you can just keep running these two different algorithm variants on your machine. So you run it overnight, and you get another run of A. The next night, you run your evolutionary algorithm again, but now in B mode. You get something that looks like this, and you keep going, another A, another B, another A, another B. And if you get enough runs of A and B, even without any statistics, you should be able to see from a set of fitness curves like this whether three conditions hold. Either A is worse and B is better. So if you got something that looked like that, that's proof that adding the hidden neurons actually made it easier for the evolutionary algorithm to evolve fast travel for the robot. Or you might get something that looks like this. What happened in this case?
Made it worse.
It made it worse. Why might adding hidden neurons actually make things worse? We're Homo sapiens sapiens, right? We're brainiacs. Obviously, big brains are good. Not always.
There's more variables to change, so it might take longer for the random algorithm to find a good combination.
Absolutely, right? There's just more synapses, meaning more synaptic weights, meaning a higher dimensional fitness landscape. There's just more space for the evolutionary algorithm to have to search through. When we're running this on your machine, you don't have infinite time. We're cutting off your evolutionary at a certain period of time. So even a result like this or like this doesn't necessarily mean that A or B is better in general. It just means given the computational budget you allowed for the algorithm, this amount of time, which is maybe 8 hours on your laptop overnight, this is what you're able to get. Yeah? Okay. A third possibility is this. It neither hurts, whatever you did in B, it neither hurts nor helps. This is perfectly acceptable at the oral presentation at the end of the semester. It's not up to you whether you get this or this or this. It's up to Mother Nature, whatever is actually the case. So you're not running your final project to try and get this situation. You're not trying to set up your system such that hidden neurons are better for the evolutionary algorithm. You're operating in this class not as an engineer, but as a scientist. You just want to see whether subjugating some aspect of the system to evolutionary control helps or hurts. That's it. Okay. So at the end of the semester, we want to see for everybody's project either this, this, or this, but not this. We just don't have enough runs here to conclude anything. Yeah? Okay. Some of you have faster laptops than others, so we're trying to level the playing field here, right? So make sure you start collecting data soon enough. If you start collecting data the night before you have to present your final project, you're definitely going to have this situation, and you're going to come to class and say, I don't know actually what the situation is. If I had done more runs, it might have been this, it might have been this, or it might have been this. That's not what we're looking for. Okay, some of you may have taken a statistics class, and you may be able to take your data and actually say something concrete with confidence intervals and p-values. Statistics is not a prerequisite for this course, so if you want to talk p-values and confidence intervals, you're welcome to do so. If you're not comfortable with that language, make sure you get enough data so that we can just see which of these three cases is the case. Make sense? Questions? Comments? No? Okay. All right, back to lecture material. So we're going to dive into evolving bodies and brains today. As promised last time, we're going to start by looking at rigid robots. So we're going to rewind the tape again, go back to 1994, and we'll end the semester by looking at evolving bodies and brains for xenobots. This is an ongoing area of research, and we published the latest paper about xenobots last month. So we'll take you right up to the bleeding edge by the end of the semester. Okay, let's go and have a look at the evolution of bodies and brains of rigid robots, which was published in a paper back in 1994. This is another paper that is often pointed at as the beginning of the field of evolutionary robotics. I've been telling you throughout the semester that physics engines weren't invented until the year 2000. Carl Sims, who did the work we're going to look at today, a very talented computer graphics researcher and an incredible coder. He coded up not just an evolutionary robotics experiment, which was kind of a new idea at the time, but he also realized he needed to evaluate all of these robots not in reality, but in the computer somehow. So he also invented physics engines and made his own physics engine. Okay, let's have a look at some of the results of Carl Sims's evolved virtual creatures. I've seen this video many, many times. It's often hard to remember. This is 1994, way ahead of its time. What are we looking at the evolution of? Sea life. So swimming, not walking in this case. A lot of cases of, I guess, what you would consider perverse instantiation. Maybe, maybe not. You can tell that the bodies are being evolved along with the neural controllers inside these robots, because these are probably not bodies that any human engineer would ever dream up. But they get the job done. Kind of. So we're looking at the Hall of Champions, the best of the best at the end. Some for swimming, some for walking. You saw a couple for high jumping early on. I know some of you are tackling the Up, Up, and Away project. You'll notice the shadows. You'll notice there's also a little bit of reflectance. Remember, this was a computer graphics researcher. This is, remember Phototaxis and the Bratenberg vehicles? This is a version of that. You can tell by the movement of the red dot, he's controlling it with a mouse. So this is real-time behavior after evolution has occurred, playing back the most fit solutions. We're going to talk about this in a few minutes. This is coevolution, which we haven't actually talked about in this class, where the fitness of one of these individuals is dependent on what that individual does, but also on the behavior of the other individual. You can probably guess what the fitness function is here. Minimize your distance to the block and maximize the distance of the other robot's distance from the block. You're looking at what's known as a coevolutionary arms race. I come up with a good solution. My competitor comes up with a solution to my solution. I come up with a solution to his solution, and so on. A really good solution, which of course then starts to propagate through the population, leading back to stalemate. This has got to be my favorite. Ignore the block and just, beat up on your competitor. Or just give up altogether. Okay. There used to be an annual workshop in our field, which is you had to come and bring your current research and try and prove that you've done better than this. Very difficult to do. Carl set a very high bar very early on for all of us. Okay. Okay, so let's have a look at how this achievement occurred. We're going back to 1994. So in the very early 1990s, there was a company called Thinking Machines by Danny Hillis. Wrong button. Trying to get the lights to come all the way back up. What am I missing here? Okay, good enough. There was a company called Thinking Machines by Danny Hillis, and he was creating some parallel supercomputers. There was, as you can probably imagine, Connection Machine 1, 2, 3, 4, and eventually Connection Machine 5. That was so powerful in the early 90s, there weren't a lot of applications that could demonstrate the power of this machine. So Thinking Machines was looking for a killer app, something that would demonstrate to the larger public that there's a use for these kinds of machines, these parallel machines. So why is it called the Connection Machine 5? It was the version number, but it was also a nod to the parallel architecture of this machine, which was having 1,024 cores inside, and every core was more or less directly connected to 5 other cores. Think of that kind of connectivity. That turned out to be a pretty good way to do things. And it turns out that when you ran the CM5 back in the early 90s, it would get a speed of 131 giga floating point operations per second. Not bad. I made this slide a few years ago, and at that time, my Mac Pro, what would that have been, the 2019, 2020 Mac Pro clocked out at about 91 gigaflops. So not bad. This machine that filled up an entire room had about the speed of a high-powered Mac just a few years ago. Not bad, actually. So powerful, again, what would you ever need such a thing for? The government had a need for these kinds of machines, as you can imagine, but Thinking Machines could only sell so many of these to the government. They wanted to sell them to the general public, so they needed a whiz-bang killer app. So they hired Danny Hillis, a very well-known computer graphics researcher at the time, to create something visually compelling that clearly required a lot of computation and would demonstrate the power of this machine. For the movie geeks that are here, in Jurassic Park, the machine that you see in the background, those are a couple of actual Connection machines in the movie. You might have noticed that there's about 1,024 blinking lights on the front here. This is showing when any one of these cores is actually conducting a floating point operation and when it's quiet and waiting for input from its 5 neighbors. Okay. So Sim sat down, and remember that at this time, evolutionary algorithms had been around for decades. So the idea of evolutionary algorithms was around. The idea of virtual creatures, you remember when we saw the Boids? That was mid to late 80s. So the idea of the Boids was around, and they had the sort of separate, align, move towards. The idea of evolutionary algorithms was around. Carl kind of brought these two ideas together, and the result was the video that you saw. We'll start to introduce some experimental details. The results that you saw in the previous video had a population size of 300, ran it for about 100 generations, and that required about 3 hours on the CM5. So not bad. 3 hours, that meant Carl could do a bunch of A/B tests. So he could collect 5 runs of A in 15 hours and then collect 5 results of B in 15 hours to see whether that mutation operator that he put in produced robots that were better at grabbing and keeping the block or not. So he was able to iterate, not quite in real time, but almost in real time. Okay. All right, let's dive in and look at the evolutionary algorithm itself. This is probably the most complicated evolutionary algorithm we're going to see in this course, so we'll take our time. Remember that in an evolutionary algorithm, we have a population of genotypes, and these are data structures. And when we evaluate any one of these genotypes, we translate that genotype into a phenotype, and then evaluate the fitness of that phenotype in some way. In your case, your genotype is a vector of floating point numbers. You translate that into a phenotype, which is a set of labeled synaptic weights sitting inside your virtual robot. And then, like Carl, you evaluate the fitness of that robot, and that fitness value gets assigned back to that genotype, that string of numbers. We've seen genetic programming a few times in this course now, a particular type of evolutionary algorithm. In genetic programming, the genotype is not a vector of numbers, it's a tree, where a tree is made up of a root node, as we've seen before. It's got a bunch of edges. Each of these edges has a node hanging off the edge, and so on. This is the data structure type for the genotypes in genetic programming. And just last class, we saw this turned into a bunch of lions that are trying to bring down a gazelle on a virtual toroid. Yeah? Genotype, phenotype. This is a relatively complicated evolutionary algorithm because the data structure encoding the genotypes for Carl's virtual creatures are nested, directed multigraphs. So we got 3 adjectives, nested, directed, and multi, that we'll have to get through. The graph part, hopefully, is not too difficult. A graph is a general data structure that's made up, like trees, of a bunch of nodes connected by a bunch of edges, like you see here. A tree is a particular type of graph. A neural network, which is sitting inside your virtual robots, another type of graph where the nodes represent neurons and the edges represent synapses. This is not a neural network. This is a graph that's encoding instructions for how to build a robot. This data structure or genotype or blueprint describes how to build this thing. This genotype describes how to build this thing. This genotype describes how to build this thing. Genotype, phenotype, genotype, phenotype, genotype, phenotype. We're going to talk in a moment about the arrow, the mapping, the way that this genotype is turned into a phenotype. The phenotype, as always, is a simulated robot with a particular morphology and controller. What's important, what's at the heart of what we're looking at today, is the genotype has instructions about how to build the body, which obviously you can see, and the neural controller inside the body, which you can't see in this picture. We'll have a look at it. Okay, the mapping that we're going to look at in a moment is recursive. I know not everybody in this class is a computer scientist, so some of you might not have come across the concept of recursion before. It's a bit of a difficult concept when you come across it for the first time. So again, we're going to take things slowly. Any questions so far? So far, so good? Okay. All right, let's head down into the engine room. The genotype, remember, is a graph. The graph is made up of a series of nodes and edges. What is not shown in this picture is every node and every edge has associated with it a number of labels. And these are the bits of the blueprint, the things that describe how to construct the robot. Here are all the labels that are attached to every node. Here are all the labels that are attached to every edge. Let's take these one at a time. The first set of labels inside a node is body part dimensions. We're going to restrict ourselves today to rectangular solids. So a rectangular solid has a length, width, and height. The thing that's inside a node label is, the first thing that's inside this is a triplet of floating point numbers dictating the length, width, and height of the rectangular solid that is being built by this node. So let's use this genotype and this phenotype as our example for now. Inside this node is a certain length, width, and height. When we start along this arrow, when we start constructing this robot, we have to choose some node in the genotype to start. This is usually, there's a special node that's chosen as the start node. We can draw this a little bit better. This is often drawn like this, where you have a series of nodes. One of them has a double outline that's indicating the start node. In this particular graph, there's only one node, so we know which one is the start node. It's this node. So we're starting here. We are the ones who are going to translate this genotype into the phenotype. So we look inside this node, and we see a particular length, width, and height, and we build a rectangular solid of that length, width, and height, like this. Okay. So we've got our rectangular solid. I'm going to ignore these other ones for a moment. We'll come back to them. We've built this piece, so let's build the rest of the robot. You'll notice that we've got edges that have arrows on them. That's the directed part. So this is an undirected node. This is an undirected graph. This is a directed graph. We're dealing with directed graphs today. So we've built this segment, and we are now going to move outward along both edges, which is hard to wrap your mind around. So we're going to simplify things today. We're going to think about following one edge and then the other edge. Let's follow the left, doesn't really matter. Let's follow the left edge first. As we move out onto this leftmost edge, we encounter another set of labels. The first set of labels are deltas, or changes. They dictate change in position, orientation, and scale. Okay, change in position, what does that mean? It means some of the labels that are sitting on this edge are delta X, delta Y, and delta Z. We just placed this rectangular solid here. So we have an X, Y, and Z, which is the center of this rectangular solid. We take the three deltas here and we move to that new position relative to this position. So we've moved a position. We're about to place a new rectangular solid at this location. We're going to also take out another three numbers, which are change in orientation. You may or may not remember when we talked about physics engines back at the beginning of the semester, we talked about using three numbers to dictate the orientation of an object in three-dimensional space. Strictly speaking, we need 4 to encode a quaternion, which exactly dictates a change in orientation. That's what's in here. There are actually 4 numbers that are representing a quaternion, not necessary for our discussion today. So we'll just think about the second set of labels as change in yaw, pitch, and roll, which I always get confused, right? It's one of them is this one of them is this one, and one of them is this one, yeah? So think about, we just created this object. Imagine you create an identical copy of this object. We've just changed its position, we've changed its orientation, and then we've changed its scale. We're going to increase or decrease L, W, and H, length, width, and height, which I can't do with my eraser here, so you'll have to just imagine that. Yeah? Okay, so we now have a new object at a new position, a new orientation, and a new scale. The last thing we do is we don't want these objects separated, so we just move them so that they're touching. That gives us this particular object that you see here. So far, so good? Okay, let's pause for a moment. We just traveled out along this edge, which actually took us back here. But let's pause for a moment and go back. We had built this one. We just built this one. Let's go along the right-hand edge. This right-hand edge has its own set of labels, another set of changes in position, orientation, and scale. When we travel out along this edge, we follow those instructions and then place this object as well. So we visited this node, we followed this edge, we've collected a bunch of deltas, and when we've come back to this node, we built this piece. When we left this node, after building this piece, traveled out along this edge, we collected another set of deltas, and when we came back to this node, we constructed a new piece, but we did it with a new position, orientation, and scale to place this piece. Everybody see that so far? So every time we land inside a node, we construct something, and we construct it based on the information inside the node and the information we've collected along the edge. Okay. All right. So here comes the recursive part for those who haven't seen it before. So we built this piece. We followed these two edges and brought us back here to build these two pieces. Let's just follow the left branch. So we built this piece, followed the left edge, built this piece, which brought us back here. This node, again, it's got two outgoing edges. So again, we follow the outgoing edge, and now we build this piece, which brings us back here. We follow the edge again, builds this piece. Brings us back here, we follow the left edge, builds this piece. If we kept running this mapping algorithm, I'm describing an algorithm to you, that's what's inside this arrow here, what would happen? You get a full circle or a spiral that would go on forever, right? How do we know when to stop? We indicated a start node where we started the construction process, and we're now sort of moving through this maze. It doesn't look like a maze, but we keep following these edges and coming back to the same node. Every time we arrive at a node, we build a new piece.
Repeat the recursive limit.
The recursive limit. So for those that aren't familiar with recursion, we're starting with the problem, which is if we implemented this algorithm, it never stops. It'll build an infinite number of nodes, which, as you know very well, is not going to run very well in a physics engine. Yeah? So in recursion, we build in something known as the recursive limit or the base case, which is some way for the algorithm to say, I'm exhausted, I'm done, that's it. How do we do this? The recursive limit, as you see, we're going to call it RL. It is another node label. It's a number that we assign to every node. Let me count silently for a minute. Okay, we're going to set RL equal to 5. It's an arbitrary integer. The evolutionary algorithm, which we're going to see in a moment, which is assigning all of these numbers, let's assume that to this randomly generated genotype, this genome, it's assigned an RL of 5. What we're going to do is every time we build a piece and then leave a node, we're going to decrement the RL counter. So when we're here the first time, RL equals 5. We build this node, we follow the left edge, we decrease RL in here to 4. We come here, we build this piece, we leave this node again along the outgoing edge, we decrease RL to 3, to 2, to 1. And when we get here, when we come back again to the node, so we're sitting here, we've just built this piece, we follow the left-hand edge and come back to here, all ready to construct something, but now RL equals 0, and when RL equals 0, we don't follow all outgoing edges. We're done. That's the recursive limit. Okay. We remember that when we leave a node, we actually follow both outgoing edges, which means we come back to the same node twice, which decrements RL. So it's not actually 5, it's a much higher number. What happens if RL is a much higher number? It's set to RL 100. Let's assume that's the only change we've made to the genotype here. How does that change the phenotype? Generally speaking. What is this tree-like robot going to look like?
Just bigger and more full.
Bigger, full, leafier. If we pulled RL to, what if RL was equal to 1? What would this tree look like? We start here, we build this thing, we decrement RL.
And just the first like stick.
It's just the trunk, right? That's it. Because the minute we leave this node, we decrement RL from 1 to 0, we just build the trunk. So imagine RL, whatever the number of RL is, builds this thing. Assume that this thing can crawl along the ground and actually get a pretty good fitness. It survives in the population and produces offspring. As always, when we produce offspring, we make a randomly modified copy of the genotype. We make a copy of this thing, and let's assume there's a random mutation that increases RL in the child. The child is going to be a tree like the parent, but it's going to be leafier than the parent. If that child produces 7 grandchildren that have different RL values, they're all going to be trees that are leafier or less leafier. Everybody see that? Okay. All right. So far, so good. Remember, Carl Sims is a computer graphics researcher, so we get things that look pretty, but this isn't necessarily evaluable in a physics engine yet. We're missing some things. What are we missing?
You need the brain to control it.
We need the brain to control it, and other ideas?
Like motors and sensors.
Motors, sensors. The motors control the hinge joints. We need joints as well, right? So far, we've only described what in PyBullet are links. So if we put this thing inside a physics engine, it would just fall apart into a bundle of sticks, right? There's no connections between these things. So more details, that's why it's so complicated. As we're traversing this graph, we are also welding or connecting the parts that we're building together with joints. You'll notice there are some joint labels in here. So every time we're at this node and we build a piece, we look to see whether this piece has a parent piece or a parent object or a parent link. What does that mean? It means that recently we've built another piece. So for example, let's start the transition again. We're here at the start node. We build this piece. This piece has no parent piece. It's the first piece we've just built. We've built that piece. We remember that we built this piece. We follow the left-hand edge. We build a new piece. And this algorithm, this mapping, remembers that this piece we just built, its parent piece is the piece we just built previously, just before we followed this edge. So at that moment, when we build this child piece, we connect the child piece to the parent piece with a joint. We connect it together. But the physics engine is going to want to know, what kind of joint do you want me to connect these two pieces together with? Do you want it to be a hinge joint? Do you want it to be a ball and socket joint? Do you want it to be a linear joint, which is what's used to approximate a piston? We don't know. So there's another label here, which is an integer. An integer of 0 says connect them with a hinge. An integer of 1 says connect them with a ball and socket. An integer says connect them with a linear joint, and so on. So as we're traversing this graph, we're building and linking together all of these pieces. Okay, a lot of algorithmic detail here. Questions, comments? So far, so good?
Can you control kind of the flow of the recursion? Like, could you have a variable that sometimes, instead of subtracting one, it maybe halves the remaining steps, or decides to go a different direction in terms of depth?
Absolutely. Great idea, right? So in this example here, this simple example, everything's going to be, as you can see in this tree, everything is built to the same depth because everybody's inheriting the same recursive limit. You could set things up like have a left limit and a right limit, and they're different. Or instead of decrementing it, there might be an operation sitting on this edge that says subtract 1, which is what we have hard-coded, or divide by 2, could be something else, which would now give you a tree where branches on either sides are of different sizes. You could complicate this algorithm if you want. Some students in previous years have tackled this as a final project. Surprise, surprise, this is a hard project, not an easy project. Doable, but there you go. Questions?
I don't get the terminal flag part.
We haven't got to the terminal flag yet. We'll get there. Yeah, it's a little tricky. So far, so good? What does joint limits mean? Let's dust off your physics engine knowledge. Idea? Exactly, right? So your elbow, for good reason, has a limit, right? Same thing with your knee joint. You go past that limit, you're in a lot of trouble. So by encoding these, by adding these as labels in the genotype, low values mean a restricted joint. Higher values mean a joint with more swept area or volume. Yeah. Okay. These are getting into like the details of physics engines, but you're all physics engines nerds at this point, so you'll appreciate these details. Okay. I think we've covered all the node labels here. Let's jump to the edge labels. Remember, most of the edge labels are deltas. They're dictating changes. We build things at the nodes, and we collect changes in how to build things when we follow edges. Here's another change, reflection. This is a binary label. It's either 0 or 1. It means whatever you built before, reflect it 180 degrees. So Carl is building in here the things that help to favor bilateral symmetry or branching symmetry. Where have we seen this idea before? We've seen another evolutionary algorithm where the inventor built in a bias, something that biased the evolutionary algorithm to tend to produce things that are symmetric rather than just random collections of things. Where did we see that before? Remember HyperNeat when we were HyperNeat paints patterns in 2D space, 3D space, higher dimensional space. The way in which HyperNeat was built, that evolutionary algorithm, doesn't paint random patterns into spaces of various dimension. It tends to produce things that have symmetry and repetition and so on. This algorithm also tends to bias evolution towards phenotypes that have reflections and symmetries, as you can see here. Okay, we've almost come to the terminal only flag. Before we do this last label, let's build up our intuition for this algorithm. It's pretty complicated. Let's take this genotype over here. We already have the answer. We know what it builds. How? How does it build it?
You're starting with the body segment. It's going to take an edge that's what's going to find the body segment.
Okay, so yeah, let's do this a point at a time. So this is probably the starting node. It builds this body segment, for example. Then where are we going to go next? The left, center, or right edge? Doesn't really matter which order we follow them in. One of the nice things about this algorithm.
And they'll take either one and it'll either...
Well, you tell us. Let's take us on a tour. Which one?
I guess just start with going through all the body edges then. They'll take
Okay.
the body edge,
Come back here.
find another body.
It's going to build this piece.
Yep.
We
Then
follow,
do the next one.
and it's going to build this one.
And at that point, it's hit the recursive limit for that, which would be, I guess, 3.
That's it. So we visited this node 3 times, and we've built these 3 pieces. What we haven't described yet, because we can't describe everything at the same time, is every time we visited this node, we also have to go along these 2 edges. What happens in that case?
And that case, you've got 2 arrows going out to the leg segment, so each of those indicates the separate leg going off of each side.
Exactly. So these 2 edges, I follow this one and I build this leg segment. I follow this other outgoing edge, which has different deltas. It dictates different changes in how I build things, which builds the other leg segment on this side. So I've now got this piece, this piece, this piece, this piece, and this piece. Let's go back to this piece. We just went along here and built this leg segment. What happens now?
It's going to follow its self-edge to create the connected leg segment.
This piece. So this self-edge says, build another leg segment. Okay, I built it. It's different from this one in position and orientation because there were some deltas sitting on this edge. I don't build any more because I probably hit the RL limit in here. The RL limit in here is probably 2. 2, 1, 0. Okay, you can hopefully fill in the rest of this mapping on your own. Yeah. Same thing down here. If you look at this drawing, hopefully you can intuit that there's 3 basic building blocks. This building block repeated 1, 2, 3, 4, 5, 6, 7, 8 times, and then this third building block that's only built once. Everybody get the game? Okay. It might be nice in the case of our insect over here or our humanoid over here is to have a specific little thing hanging off the end of these arms and legs that's different. But we don't want to build that little thing at the end of every limb segment. We only want to build it at the end of a series of limb segments. Now we're at the terminal only node. There's another flag. It's a binary flag 0 or 1. It says when the parent RL gets to, recursive limit gets to 0. So when we're done building a series of things, like for example, this series, or this series, or this series, when you exhaust the RL limit of that, build one special thing. Follow a special edge that leads to a secret node that you only ever follow when the parent node, the thing that's upstream of the secret node, when that RL's limit is exhausted. So this is curl, I would say, kind of cheating and kind of hacking and making it easier for the evolutionary algorithm to put hands or fingers or toes or grippers on the end of appendages. Whether it's needed or not, I don't know. Okay. All right, so we've talked about the mapping now. We know how to build the phenotype so that we now have a collection of objects connected with joints. But as you've already said, we're missing a bunch of things. Remember our list of 6 things: links, joints, sensors, motors. We don't have yet neurons, synapses, the brain. Okay. A lot of technical detail today. Pause for a moment. We've covered the body. We're now going to switch to the brain. Any questions so far? Okay. To cleanse our palate, let's play a little game. Here is 12 different phenotypes. With pen and paper or whatever you have in front of you, pick one of them and see if you can reverse engineer it. Can you draw the genotype that you think produces that phenotype? We don't have a lot of time today. I would suggest just draw the nodes and edges. You don't need to reverse engineer the actual labels, but have a go at 1 or 2 of these. And we'll give you maybe 2 or 3 minutes to do that, and then we'll see what you came up with. There's the list of labels on the right that hopefully will help you get the idea. Some are easier than others. Okay. Which one or which ones has the smallest genotype, the fewest number of nodes and edges? And why do you think that's the case?
I'm gonna go with,
I think it's 10. It's got one parent node, 4 edges, and 1 edge node.
Okay. One parent node, one child node, and what'd you say for edges?
4 edges.
Like that?
Yeah, directly.
Okay. Other ideas?
Me,
Sorry, which one?
I think number 9.
9. Okay. What does the genotype look like, very generally speaking?
So you have one, or you have the recursion going to the little tail thing, and then a terminal only flag for the bigger.
For the bigger piece. Okay, yeah, maybe. So we've got one node representing the tail segments, and then a secret node down here that represents how to build the head of this thing, possibly.
7 maybe as well.
Why 7?
It's kind of similar to 9. It seems like it's got one node and it kind of.
Okay, so possibly one node, and then these are all related? Maybe? Maybe they're all actually one. If you kind of squint, it looks like each one is sort of a little bit smaller and a little bit thinner than the other. Possibly. Same thing with like this one, maybe. If you want to create a snake, you can do it with one node and one edge, right? Make one piece and then keep applying the same change to that piece along the growing length of the snake that you're constructing. Okay, let's tackle one more. Somebody want to try and give me one, and we'll try and describe its genotype in a little more detail?
3 nodes. Oh, this is for number 2.
Number 2, okay?
3 nodes, a body, an upper arm, and a lower arm node.
Okay, how are they wired up?
You start on the body, and then 2 arrows to the upper arm, 1 arrow from the body to the lower arm, and then 1 arrow to the lower arm, from the upper arm.
One from the upper arm to the,
Lower arm?
maybe. Could work. Other ideas for the same robot, different robot?
I would have 3 nodes, or, 3 nodes.
For the same one?
Yeah.
Okay.
With just like, fin and then arm, so body, fin, and arm.
How are they wired up?
So,
Can we start at the body?
Yeah, body goes to fin directly, and then body also goes to arm, which goes back to itself.
The arm goes back to itself. So talk me through the arm. Are these the arms?
That's what I was gonna do.
Okay, so we're here, and you want to build, we've got to build 2 arms. So we're going to follow this to here.
And then it goes right back to itself.
Okay, that'll build an upper fin and a lower fin.
Oh, need 2 from body to arm.
That's it. That's it, exactly. Okay, I think you're getting the intuition here. Okay, shall we move on to brain? Okay, deep breath, here we go. All right, we've covered, sorry, I'm going to back up for a moment. We've talked about the fact that this is a directed graph. What is a multigraph? A multigraph is a graph in which pairs of edges can have one or multiple edges going between the same pair of nodes. For various reasons, most graphs tend not to have this structure. Here we do have it. So a multigraph, multiple edges can leave one node and they can all arrive at the same other node. Yeah, that's what makes it a multigraph. So we've covered directed multigraphs. These graphs are also nested, and I already gave away the punchline here, which is nested graphs. If you zoom in on any one node in the graph, there's another graph inside. There's multiple nodes and edges inside any given node. So here we go. We're going to work with this particular phenotype over here. We're going to look at how this genotype constructs the body of this robot and the brain simultaneously. Okay, you notice here in bold, we've got everything we just talked about. The bold is the stuff that builds the body. Okay, let's start with this piece over here. It's not clear from this figure, but this node, this bold node constructs the body segments. You can see there's a self connection. So build this body segment, follow the self connection, build this body segment, hit the recursive limit, stop, go back to each node that you visited, follow these outgoing edges to build the left and the right fin. So this is body node, fin node. Everybody see that? We can construct the body. Okay, let's go back to the beginning. When we built the first body segment, we obviously built it, and then we put inside it 3 neurons, 1, 2, 3. So the nested graph, the graph inside the other graph, is going to tell us how to build the neurons and how to wire those neurons up with synapses. This particular genotype is telling us to drop 3 neurons, 1, 2, 3, inside this body segment. And you'll notice there's some weird cryptic words inside the neuron nodes. You're all neural network experts at this point as well. What do you think these represent? They're more build instructions. They're telling us how to build the neurons. I'm not talking about synapses yet. Hint, hint.
Are they the kind of like sensors that will be?
Not the sensors. We're not there yet.
They're the activation functions of the neurons?
They're the activation functions of the neurons. Remember, whenever we build a neuron inside ChatGPT, inside a robot, we've got all these incoming edges. We take the raw weighted sum, right? The presynaptic value times the synaptic weight plus another presynaptic neuron's value, its synaptic weight, add them all up, we've got a weighted sum. We take that raw weighted sum that's arriving inside a neuron, and we push that through an activation function. So in the activation function, on the horizontal axis here, we have the raw weighted sum. On the vertical axis, I'm just going to be lazy and call it y. It's the value that that neuron actually outputs. If we have the identity activation function, whatever the raw weighted sum is, it'll output that raw weighted sum as its output. A lot of machine learning researchers have expended a lot of blood, sweat, and tears coming up with fancy activation functions. In this case, Carl has just turned over the task to the evolutionary algorithm. Anybody want to take a guess at any of these?
ABS is probably just absolute value, like really.
Absolutely. It's the absolute, yep.
WAV, I think, would be a sine wave. Seems like wave.
Waves, yeah. So technically it's
Okay.
hard to know, but waveform. This one, I don't even remember. You got to go back and read the paper. But you get the idea, yeah? So as we're traversing this graph, we're dropping neurons into different parts of the body. When we build the fin, every time we build one of these 4 fins, we drop these 6 neurons inside. So let's do a neuron count. 3 in here, 6, 12, 18, 24, 30 neurons. So you're looking at a 6-segment, 30 neuron robot so far. So far, so good? Okay. We're still missing a few things. So we now have links, joints, neurons. We missed motors and sensors. So you'll notice that when we built the fin here, we're dropping these 6 neurons, and some of the nodes that tell us how to build these neurons, they don't have activation functions inside. These are activation functions. Some of them say J0, J1. What does that mean? J for, what have we built so far? So the J stands for joints here. So we're creating a neuron and attaching it to a joint that connects this piece back to this piece. It's very cryptic here. These are the motor neurons. So the inner graph is creating different types of neurons with different activation functions. And sometimes it also says, and this is a motor neuron. This is a motor neuron. Attach it to this joint. I'm sorry, I misspoke. The J does stand for joint. This is dictating a proprioceptive sensor. Go get the angle of the joint and drop it into that neuron as the robot is swimming around. So these are being dictated by the genotype as sensor neurons. J0 and J1, these are referring to different joints. This is another confusing point. It turns out that in this particular physics engine, you can attach pieces together with multiple hinge joints. So one way of approximating the shoulder joint is you create this object, and you attach it with 2 hinge joints that allow this rotational degree of freedom and this rotational degree of freedom. So it's difficult to do in PyBullet. It's not impossible. Also not so important for our discussion today. Okay, sensor neurons. These, as you can probably guess, are motor neurons. This is E for effector. Roboticists have terrible terminology. We talk about motors, actuators, and effectors. They all mean the same thing. Yeah? Okay, so the values arriving at these motor neurons inside this fin, for example, 2 values arriving at 2 motor neurons. Those 2 motor neurons send forces to the 2 hinge joints that connect this fin back to the main body. There's another 2 sensor neurons and motor neurons inside here, another 2 sensor and motor neurons in here, another 2 sensor and motor neurons in here. So far, so good? Okay. You can probably guess what the nested edges are doing inside the outer nodes. We're over the hard part now. What's left? We've covered links, joints, motors, sensors, neurons, synapses, right? Okay. So this little arrow here, for example, says connect this hidden neuron. It's not a sensor neuron. It's not a motor neuron. It has greater than, which is a type of activation function. Connect this hidden neuron to this motor neuron. So this synapse shows up in here, in here, in here, and in here. And there's a tiny label, one label, sitting on this nested edge. And that label represents the very last piece that we need before we can start running this thing in a physics engine. The weight. Okay. Let's talk about the elephant in the room. What is this thing up here? Okay. The dashed piece here dictates that this is a node that's visited, but it doesn't build a body part. It only builds one set of whatever neurons and synapses are inside this special dashed node. And every genotype, it's not shown in this picture, every genotype has one and only one dashed node. So we've got bundles of neurons and synapses that are being copied. We've got little neural circuits. Here's one neural circuit. Here's another neural circuit. They're being cloned and placed in different parts of the body. And then one special neural circuit that's only built once. What does that sound like?
Sounds like a brain.
Like a central brain.
Central brain, specifically the central nervous system, right? You have one, I have one, it's in here, right? You have one and only one copy of this. Your peripheral nervous system, there are all kinds of little bundles of neural circuits that all look almost identical to one another, and they're aligned vertically down your spine, down your arms, down your legs, across your fingers. Not surprisingly, your fingers have the same kind of bundles of neurons and synapses inside. Your peripheral nervous system, peripherally, it's a big collection of a lot of very similarly copied things. So this was Carl's way of approximating or giving each one of his robots a central nervous system and a peripheral nervous system. Our good friend the octopus, which is always an exception to every rule, it's mostly peripheral nervous system. It's got big bundles of neural circuits. Guess how many it has? Right? And then there's a very, very small central nervous system, but it doesn't do much, right? Mammals and primates, and specifically us, we are very much CNS heavy and PNS light. Okay. All right, so that's our non-local brain, and that covers the nested part. Question?
Why do you think, like, is there evolutionary pressure that would cause something to have a peripheral nervous system?
A wonderful question. So we can ask that question about biology. Why do some species have a lot of PNS and very little CNS, and why do other species have the opposite? There must be evolutionary pressures that favor one solution over another. One of the things that could have been done with Carl's evolutionary algorithm is look at whether or not central nervous systems evolve in his virtual creatures. Do you need one for scurrying over flat ground, or swimming, or competing with a competitor over a block? Unfortunately, he never reported it. If you're feeling ambitious and you want to try and re-implement Carl Sims, we're all ears. We'd love to know what the case is. Nobody knows. In biology, there are arguments and hypotheses about why, but it's still very much an open question. We have a huge CNS. What's it so good for?
Strong, like that critical thinking, and I know the peripheral nervous system is a lot more common in animals that can regrow. So octopus,
Yeah.
starfish, don't have like as big a central because if they lose a limb, they've got to still be able to regrow, and it's got their entire central nervous system that can't really.
Yeah, absolutely. If you're distributed and you tend to have a lot of limbs and you tend to lose those limbs a lot of the time, don't put all your eggs in one basket in case the basket goes missing. Then you're in real trouble, right? So yes, you can make arguments about what kinds of evolutionary pressures. It's a good hypothesis. How do we test it? In biology, we just kind of have what we have. We have octopi, we have primates, that just is. In a system like this, you might actually be able to see that process at work. Okay, we talked about all this. We talked about this. So he made this very long list of activation functions, which was kind of fun because this predated all of the arguments in the machine learning community in the thousands and into the 2010s about what are good and bad activation functions. Carl was agnostic. He said, I don't know what's a good activation function, but there probably are some that are better or worse than others. I'm going to let evolution figure it all out. Okay. Any other questions about this complicated evolutionary algorithm? Okay, we got 5 minutes left, so we're going to try and finish off this lecture today. This is the unrolled nervous system for this creature. If you squint, you look carefully, you'll see 1, 2, 3, 4 bundles of identical neural circuits. Those are the circuits in the 4 fins, and 1, 2 identical neural circuits sitting in the 2 body segments, and then only 1 copy of this thing up here, which is the central nervous system. Okay. I think I'm going to skip over this in the interest of time. He came up with fancy crossover events because if we have 2 parents that survive and they have 2 different multigraphs, how do we combine them into a child multigraph that's likely to produce an offspring? He made a good effort at it. You'll remember Ken Stanley's NEAT algorithm that we talked about a few weeks back. Does a much better job at this and kind of eclipsed this approach. You saw the creatures competing over the cube. We take one creature out of the population, put it in its starting zone, put creature 2 in its starting zone, let them compete. How do we compute the fitness for creature 1? I kind of mentioned it in passing while we were watching the video. Minimize your distance to the cube, maximize the distance of the other. Same for this creature. I was going to put the math down here. You can figure it out for yourself. Why does the starting zone have this sloping ceiling? The creature has to fit inside this area. Absolutely. You can bet that Carl started with the starting zone that looked like this, and very tall creatures evolved that fell onto the block. You even saw some in the video. So if you evolve to be taller, you can be as tall as you want, but you're just going to be placed further back in the starting zone at the position just where you're going to fit inside the starting zone. So this design decision you see right here is a response to perverse instantiation. Right? It's everywhere, very hard to stamp out. Okay. Last thing they looked at is this idea of coevolutionary algorithms. So in the interest of time, I just want to look at panels E, F, and G here. You'll notice that we now don't have one population. We have 2 populations of nested, directed multigraphs. We have 2 populations of genotypes. They can produce phenotypes. And any one individual from here can compete against individuals from over here. If I do really well against you, but I do terribly against you, you do really well against me, but terrible against you, and vice versa. Which of the 3 of us is best, right? Tricky to figure out. Thanks to the NBA, they gave us round robin and tournaments and selection and all the rest of it. So you can compete 2 individuals against one another. The winner goes on to the next round. Carl tried a whole bunch of different ways to compete individuals from different populations against one another and evolve individuals that were good, could outcompete or compete well with any other individual from the other population. You can read the paper if you want. We'll leave this as optional about ways to do this. Some of these ways are computationally expensive. Compete every individual in this population against every individual in this population and vice versa. Even for the connection machine, this takes a while. There's very computationally efficient ways to do this. Everyone just competes in one trial, but that gives you a low confidence interval estimate for how well this individual is. If this individual beats this individual, we don't know that this individual is actually good in general. So we borrow from competitive sports, and there's better ways to do this. Okay. I got 1 minute left. Let's look at 4 evolutionary runs. We have the gray population and the black population. They're just two different populations competing over the cube. At this point in evolutionary time, the black robots were doing better than the gray robots. Mutation crossover, evolutionary time elapses, and now the gray robots are doing better than the black robots, and back and forth. You get interesting coevolutionary arms races going on. Here, the black robots evolved such a good strategy that we got what's called fitness collapse. From the point of view of the gray robots over here, no matter what mutations and crossover events occurred among the gray population, they just always had a fitness of 0. They were always getting hammered, probably literally, by the black robots. The fitness landscape for the gray individuals was a perfectly flat, perfectly low surface. There was no way for them to do any better. Last observation I want to make, and then I'll let you go. We've talked about a fitness landscape as a landscape. The assumption is that it doesn't change. When you have two evolving populations, they are both sitting on a fitness surface, but that surface is no longer a landscape, it's a rolling sea. I'm an individual in one population, and I'm competing really well against everyone in the other population, so I'm sitting up high on a peak. But those other individuals now start to evolve a counter strategy that beats me. What happens to me and my offspring? We find that we're sitting on top of a sand dune or a rolling wave that starts to decrease. Whatever I was doing before that worked starts to accrue less and less fitness over evolutionary time. Very interesting coevolutionary dynamics, which we don't have time for in this class. We will pause here. You have a quiz due tonight. You're submitting milestone 1 and then moving on to milestone 2. See you on Thursday.